So the third law states that for every force on one body, there's an equal and opposite force on another body. Okay? As Brehan said, if you punch a wall, the reason why your hand will hurt is because the wall exerted a force that was equal but opposite, right? It's the same reason why you can't just, push a tree over. It's because the tree resists the force that you put on it.
Well, not always equal and opposite. Like if you just break the wall, then it's not going to be equal.
Well,
right?
that's because then the wall has
it can't
an acceleration.
Exactly. So it can't provide enough normal force to counteract your punch, so it would break it, right? Exactly.
For sure. But something that's interesting, right, is that when you jump, if you just go outside, you don't even have to go outside, you can just jump. The force that you apply on the earth to accelerate your body upwards is the same force that the earth applies on your feet for you to be able to jump. And so the earth and your body are both moving away from the common center of mass with the same like transfer of energy. If that does that make sense? Like
same trans.
Like
okay.
for example, you're changing your momentum from 0 in your frame to whatever your mass is times the velocity you leave the earth at, right? But you're giving the earth the same amount of momentum, but in the opposite direction.
Momentum is a vector. It's a directional quantity. So if you are getting momentum upwards, it's the reason it's still conserved is because the earth is getting momentum downwards, right? So it'll always cancel out.
You are actually single-handedly moving the entire earth downwards by jumping. So
that's a way to think about it.
That's fun.
There was a really cool video I remember called "What if everyone jumped at once?" Like what if everyone on the earth jumped at once? The thing is, it would be a little interesting. You know why? Because the land is not symmetrical around the earth. Like, it's not equal in like the first quadrant as it is in the third, and the second as it is in the fourth. So if people jump, I don't know,
I don't think anything would happen, to be honest.
No, there's no way, because obviously we cannot push out that much force, because us jumping up is literally nothing for the earth, literally nothing. So it wouldn't really matter. But yeah, so again, another important consequence of this is understanding the normal force that you were talking about, right? Like just thinking about, okay, maybe we can talk about that later, but like thinking about just a book on a table, like why is it remaining on that table and not falling to the ground? Because the table is applying a force that is equal to the book's force of gravity. Now, the interesting thing about the normal force is that it keeps changing. It keeps changing dependent on how much weight or technically weight is the correct word, how much weight is being applied on it. So the heavier the object, the more the normal force the table or whatever will provide. Now, obviously, there's a breaking point, which is when, as we were saying, like the normal force cannot equal the gravitational force, and it simply breaks, hence accelerating the table.
But this is just a strictly like structural property of the table that you're
there's also a consequence of simply the normal force, right? Like understanding the normal force, it is obviously it is a force, but it's only a force present to counteract another force. That's the only reason it's there. The only reason it's there is to counteract something else. So it's not really its own force.